Hello, and welcome to Chapter 4, Section 5, Part 1. Today we are talking about integration by substitution, or sometimes you might hear it abbreviated as USub. So before we get into it, I want to do a quick reminder of things that we've done back in the derivative chapter. So specifically, the chain rule chapter, because what we want to do is start finding integrals and antiderivatives of more complicated things where we can't just use the power rule anymore. And so with the more complicated things, that's kind of where like chain rule popped up. So let's say we had the function e to the 5x power, the derivative of it, because the 5x part was like more complicated, we can kind of think of it as like it's in parentheses. So we would have to use the chain rule where it was the derivative of the outside times the derivative of the inside. And so like our inside part, we would call it like u sometimes. And so our inside was 5x and the derivative of 5x was just 5. So then the derivative of the outside was still e to the 5x. The derivative of the inside was 5. So multiplying those together, we got 5e to the 5x. So that was kind of like real quick recap of chain rule. So we're using these facts to kind of think about it in terms of antiderivatives or integrals. So now that we're talking about antiderivatives, basic or integrals, we're finding the integral of something like 5e to the 5x. And so remember, we're trying to think like, what can I take the derivative of to get this? Oh, sorry, I forgot to write the dx in there. So 5e to the 5x dx, the antiderivative or the integral would be e to the 5x plus c, because this part e to the 5x, if I found the derivative of that, I would get 5e to the 5x. And then we always have that plus c at the end there for the constant of integration. So let's pretend we hadn't covered or like reminded ourselves of the chain rule just now, and we just saw this problem, integral of 5e to the 5x dx. How would we be able to recognize when I would need to use this thing called USub? So here, we want to start being able to recognize like, okay, I have something more complicated in the x section, like 5x. So that's something where I would have used chain rule to begin with. And then you want to quickly think about like, okay, the derivative of 5x would be 5, and that also exists in the problem. And so that's something we want to pay attention to now as we're trying to find integrals. So here, if I know the more complicated part of the x here is 5x, we're going to use u equals 5x and still find u prime like we used to do, but instead I'm just going to write this as du over dx equals 5. Because, you know, another way to write u prime was something over dx. So du over dx, which really means that I can multiply both sides by dx to get du equals 5 dx. The reason why I want this is because, do you see how, like, in my problem I have that dx there? I actually want to get dx by itself because my goal with USub is to rewrite my entire problem only in terms of u instead of using x's. So I'm actually going to rewrite this, what I have the du equals 5 dx one more time to get dx by itself. So I'm going to divide both sides by 5. So now I'm going to come back to my original problem. So I have the 5 to begin with, but now instead of writing e to the 5x, because I said u was equal to 5x, I'm going to rewrite this as e to the u power. And then for the dx, I'm going to replace this with du over 5. So I'm just substituting it in, and this is why it's called USub, because we're substituting things back in. Because now when I simplify this, the 5 and this 5 down here cancel out, because when you multiply everything together, they cancel. So really what I'm finding is just e to the u du. And so now I'm just finding the integral or the antiderivative of e to the u. So like think of this as just another variable. Instead of x's, we're dealing in terms of u, and there's like this u is nothing complicated about it. So the antiderivative would just be e to the u again. E to the u plus c. So our final answer, though, we never keep it in terms of u. We would like substitute the x's back in because our problem started with x's, so we need to end with x's as well. So replacing my u with the 5x that it was equal to, I end up with e to the 5x plus c as my antiderivative. And I know this was like a long roundabout way to get there, but because we had already talked about the chain rule for this, and that's why it took us a little bit, but we were able to get to our antiderivative, even though we kind of already knew it already. So let me do another example, this time without talking about the chain rule first. So this time we're looking at the integral of 2x times x squared plus 1 squared dx. So again, we want to be able to recognize, like, this is something we would have used chain rule for because we have parentheses, there's like complicated stuff inside the parentheses, and that's usually what we set u equal to, or like the derivative of the inside. So here, using u sub, we're going to say u equals x squared plus 1, which is also good because if I were to find the derivative of this really quick, the derivative of x squared plus 1 is just 2x, which also occurs elsewhere in the problem, which is helpful for us because that'll help us cancel things out. So I'm going to write this as du equals 2x dx. So I'm just skipping this step where I just wrote it as du over dx equals whatever the derivative is. And then I want to get dx by itself. So I'm just going to divide both sides by 2x. Okay, so now comes my task of rewriting my entire problem in terms of u instead of x's. So that 2x, there's really nothing I can do there until I kind of use because there's nothing like no u's I can change it into, but the x squared plus 1 squared is really just u squared because u we said was x squared plus 1, so replacing this part with u becomes u squared. And then instead of dx, I'm going to write du over 2x, which is great because now the 2x's cancel out. And so really I'm just finding the integral of u squared du. And now this is easy because this is just the power rule. So integrating u squared would be u cubed over 3 plus c. And then my final step is just to replace u with the x's again. So this would just be x squared plus 1, cube that, divided by 3 plus c. And there we go. All right, so my next example, again, slightly more complicated here because now we're dealing with trig, but also I have two parentheses here. So in regards to like which do I use for u, a little bit trickier because both of them are inside parentheses. But also remember we were trying to say like the derivative should be elsewhere in the problem. So really quickly, if you like remember your derivative rules, then we know for tan x plus 1, if you find the derivative of that, the derivative of tan x is secant squared. And then plus 1 is just a constant, so the derivative would be 0 there. So if the derivative of tan x is secant squared, then this would make more sense to use as u, because when I find the derivative of it, then that should cancel out with the secant squared that's out there. So I'm going to set u equal to tan x plus 1, so that du equals secant squared dx. And then get dx by itself. So I'm just going to divide both sides by secant squared. So now rewriting my original problem in terms of u, I have the secant squared x times u times, and instead of dx, it'll be du over secant squared x, which is great. We can cancel. And then we end up with just u du, and then we can use the power rule for that. So u squared over 2 plus c, and then substitute the u back in. So it'll be tan x plus 1 squared over 2 plus c. And there we go. Okay, so key skills here is you need to be able to recognize derivatives. All right, for my next example, we're going to get slightly more complicated again, because this time our derivative of u isn't going to be exactly in our problem anymore. So taking a look at this problem, we have x times x squared plus 1 raised to the 1/2 power dx. So don't forget, 1/2 power just means this is a radical. So if you ever see a radical, turn it into an exponent. All right, so here, pretty obvious, we're going to use u equals x squared plus 1 because that's what's inside the parentheses, the more complicated part of this problem. But if we're using u equals x squared plus 1, when we find du, the derivative is going to be 2x dx. And if you look in the problem, there's only an x there. So that part's a little bit weird, but the 2 that we're missing isn't too bad because it's just like a constant. Constants are easy to take care of. So I'm going to keep going and just find dx by itself again. So du over 2x is going to equal dx. So let's rewrite our problem in terms of u. So I've got the x there, and then the x squared plus 1 I'm going to rewrite as u to the 1/2 power. dx I'm going to rewrite as du over 2x. So this time stuff still cancels out, it's just not the full derivative. So the x can cancel out, but it still leaves me with that du over 2. So it's just a constant though, so I'm not too worried about it, because when I rewrite this now, I can rewrite this as 1/2 times u to the 1/2 du. So instead of just doing du over 2, I'm just multiplying by 1/2 instead. And it is a constant, so technically I can move it out of the integral and just not even deal with it just yet. Because now u to the 1/2, I can just apply the power rule to get 1/2 times u to the 3 over 2 over 3 over 2 plus c. And then simplifying this out, this would end up being 1/2 times 2 over 3 u to the 3 over 2 power plus c, which is really just 1/3 u to the 3 over 2 power plus c, and then just plug the u back in. So this would be 1/3 times x squared plus 1 to the 1/2 power, or sorry, 3/2 power plus c, and then that's it. So even if the derivative is not quite like exact, it's okay. Because as long as it's just a constant that's different about it, then we're good. And if it's not, then it gets more complicated, but we're not there yet. So let's do another example. All right, so this time, more complicated again. We've got 2x squared over 2x cubed plus 5 all squared. So giant fraction here. On the bottom, we can't even split up this fraction like we used to do because we have like 2 terms on the bottom and it's being squared, so way complicated. But there are parentheses, which means we know what we're using for u. So u is going to be 2x cubed plus 5 here. So that means du, when I find the derivative, is going to be 6x squared. Oops, not plus 5, because plus 5, the derivative would just be a 0. All right, so du equals 6x squared dx. And again, I see that I have a 2x squared on top of my original problem. And my derivative is 6x squared, so at least the x squareds I know will cancel out. And then we'll deal with the constants of 2 and 6 later. So if dx equals du over 6x squared, then rewriting my original problem, I'll have the 2x squared, and then I'm actually going to rewrite the bottom part of the 2x cubed plus 5 squared. I'm going to rewrite it as a negative exponent. So it'll be u to the negative 2 power, because the square is where the 2 comes from, but then negative because it's a fraction. And then instead of dx, I'll write it as du over 6x squared. So the x squareds will cancel. So this really leaves me with 2 over 6, which simplifies to 1/3 of the integral of u to the negative 2 du. And then now we can just apply our power rule. So it'll be 1/3 times u to the negative 1 power over negative 1 plus c. Rewriting this, I end up with negative 1/3 times 1 over u plus c. So the negative 1 I just multiplied with the 1/3, and then u to the negative 1 power is really just 1 over u. And then replace that with my whatever u equals, so it'll be 3 times 2x cubed plus 5 plus c. All right. And of course, for my last example, I'm going to throw in some trig. So for this problem, obviously parentheses indicate what you're going to use for u. So if we're trying to find the integral of cosine of 7x plus 5, then u is going to be 7x plus 5, which makes du equal to 7 dx. And then getting dx by itself, I can divide both sides by 7 to get du over 7. So now rewriting my original problem, cosine of 7x plus 5 would become cosine of u. And then the dx would be du over 7. So here, nothing cancels out, but the stuff that's on the bottom of du is just a constant. So I can actually rewrite this as 1 over 7 as a constant on the outside of the integral, and then find thus the integral of cosine of u du. The integral of cosine would be sine plus c. So 1/7 on the outside, and then replace that sine of u with 7x plus 5 plus c, and then that's it. All right, that's u sub. You got this. Now you can find integrals of more complicated problems, and of course we'll keep getting more complicated as we go. So I'll see you next time in my next video. Don't forget to like and subscribe. Bye.